with the picture of evolution that can be relatively well established, I think you have a better sort of roadmap for where to speculate. I think meaning is very difficult to account for in the computer metaphor, right? This is the well-known symbol grounding problem, the Chinese room argument. AI had called it the framing problem. This was sort of the reason why classical AI never accomplished true general intelligence, is because the meaning was absent. There are, of course, other things as well, but I think that's clearly one of the major things that was missing. And I think in terms of a control system, meaning is trivial. Meaning is always there.
This is Brain Inspired.
Hey everyone, I'm Paul. Welcome to Brain Inspired. Today's episode is the first of two parts of a conversation I had with Paul Cisek. The second, shorter segment will come out in a few days. Paul is a neuroscientist at the University of Montreal. It is impossible to summarize all the topics that we discuss because it's broad-ranging, but they all surround the themes that drive Paul's outlook and research. One of those themes is that examining evolution is of central importance to understand our cognition, a process that he calls phylogenetic refinement. Another of the themes is that behaving organisms are fundamentally a collection of feedback control mechanisms. And the purpose of brains is to control ourselves and the environment through our actions. You can contrast this viewpoint with how we often think of cognition as the thing that happens after perception and before movement. So we perceive the external world, and those perceptions transform the external world into representations in our brain. The next step is we do cognition on those representations. And then finally, those representations get transformed again into movements. This is a rough description of what's often called the computer metaphor of how brains work. But from those themes, we cover all sorts of topics, and it'll give you plenty to contemplate. We end today's segment of the conversation talking about consciousness a little, and in the next episode, we bring in AI and contrast Paul's approach to neuroscience with the currently popular idea to use algorithms and objective functions from deep learning to understand brains. Paul recommends about 300 or so books during the show, and I listed most, if not all of them, in the show notes at braininspired.co. Okay, that's it for now. I'll be back in a few days with the second part of the conversation. So, Paul, we were just talking, and I know that you were homeschooling early this morning before our chat.
Yeah.
I was homeschooling as well. In fact, I was so worn out from it, I actually just ran and I took a cold shower before we were Skyping here just to make sure that I was a very cold shower, just to make sure I was reset here and ready to go. So
I just got a coffee, a shot of espresso, so get myself going.
Yep, here's mine as
There you
well.
go. There you go.
So I know that we may get interrupted by your child who's playing outside right now with your wife, who's also homeschooling, and everything.
Yeah.
Things are different now, aren't they?
Things are strange.
Well, welcome to the show, and thank you for joining me here.
Well, thank you very much for inviting me. It's a pleasure.
So, what is your favorite decision-making area of the brain, Paul?
Oh, well, I've spent a lot of time in dorsal premotor cortex, but that's just because that's where my training lies. What's my favorite decision-making area? I don't know, the whole brain, I think.
Yeah, I think that should be your answer, although it's incorrect because the correct answer is frontal eye field, of course.
Oh, of course.
Yeah.
Yes, of course.
Okay, so...
Supplemental eye field, no?
Well, supplementary... supplementary eye field is is the winner in my world, but frontal eye field is where I've spent most of my electrodes have gone. So,
but you know what Doug Munoz says is that the entire cerebral cortex is just there to keep the rein off the superior colliculus.
Yeah, he's probably right. Don't you think?
He might be right. Yeah, he might be right.
Well, we're going to get into this. In fact, we have quite a bit to talk about because that's kind of the way that you're traversing the brain here from the beginnings to now. So So I guess it's hard to know really where to start, but one place to start is with the acknowledgement that, you hate cognition. So why do you hate cognition so much?
Well, I don't hate cognition. I just, no. I studied cognition in a sense. I guess I'm just saying that in my opinion, it's not a thing so much as a description of a type of behavior that we've chosen to separate from other behaviors, distinguish from other behaviors. Cognition is the things that we call cognitive. So things involving knowledge, etc. But I don't think it's a system in the brain that we can draw a border around and say, here is where cognition is, and outside of that is not cognition. I think that's what I disagree with.
So the cognitive revolution happened, and it saved us from behaviorism. And this is sort of the story that is told from modern day, looking back. So what was wrong with the cognitive revolution and just as you were alluding to, this mainstream sort of approach to neuroscience in thinking that cognition is a thing?
Well, I think like any scientific sort of viewpoint, it's a product of its own history of its time. So the cognitive revolution was a response to some viewpoints that had been going back and forth in psychology for much longer, really, than behaviorism. There has really been, since for hundreds of years, a discussion between a kind of a dualistic idea of psychology and a materialistic view of the brain. And psychology is actually the study of the psyche. Right? That's what the name actually means. It's the study of the non-material mind. That's how it was actually founded in the 1800s. And psychology was about studying the mind, this non-material thing. At the same time, of course, lots of people didn't agree with that. A lot of biologists didn't agree with that. A lot of ethologists didn't agree with that. It was a particular viewpoint that came to be very popular, especially in the U.S. and North America. And the behaviorists thought that the biologists had it right, and they wanted to turn psychology away from that, right? And they did it very dramatically, very radically in the early 20th century. And by some accounts went too far, rejecting, essentially not allowing people to discuss some things that really need to be discussed.
Well, that was not all of behaviorists, though,
no,
right? I mean, that was a subset.
Yeah, there was a subset. There was a few people that just went quite far, I think, with behaviorism. Too far.
And those are the people that we often point to historically and say that is behaviorism, right? I mean,
yeah,
it's not the whole story, so.
But, people like Tolman, who is pointed to as one of the empirical scientists who really overturned behaviorism, called himself a behaviorist. I mean, he considered himself a behaviorist, and he studied, rat behavior in mazes, etc., and just said, well, you can't explain this with stimulus response associations. You need to have internal states. And that was one of the major insights that led to the cognitive revolution. But again, it was a reaction to a reaction. We need to have these internal representations like early psychologists postulated. We need to have something like that, but we don't want it to be non-material. And I think what the cognitive revolution did is it said, well, maybe it's like a computer, because at the time, computers were being developed and they were very impressive. And I think there was a kind of a irresistible analogy that they led to, that perhaps the mind is like the software and the biology is like the hardware. And just like in a computer, those things are quite different. Maybe that's why they are so different in psychology. That's why we can study the software of the mind separately from the hardware of the brain. And that was a very persuasive idea. And I think a lot of people sort of jumped on that assumption. I think that assumption, is probably not altogether incorrect, but it led to a very specific metaphor that people have used. This idea of a virtual machine, that the brain runs programs on the neurons, much like a computer runs programs on circuits. And the programs we can talk about things like memory, storage buffers, and, file systems even. And that was what the cognitive revolution sort of talked about. And I think that took the analogy way too far. I think it said, let's just forget about the brain, which was, of course, convenient because we didn't know that much about the brain, and we still don't. Mm-hmm. And it said, well, you don't have to know about the brain. You can just go ahead and make progress anyway. Just talk about the software. And I think that was where it really went in a counterproductive direction because it got away from the brain and it built all kinds of ideas and theories that are now cognitive neuroscience is trying to connect them to the brain, and they don't fit. But why should they fit? I mean, right? If they were developed completely independently, it'd be kind of surprising if they did.
Right.
So, yeah.
You often, set up this problem in terms of in fact, you've been talking about this at least since 1999, to over 20 years ago now.
Yeah, well, that's when I started. Yeah, that was my first.
Yeah. A good one. A good first one.
Thanks.
And so you often set up the problem as the way that modern neuroscience looks at the brain is from the computer metaphor. So you were just talking about the hardware and software metaphors. But the other way that you open this is by saying that likewise, we think of the brain as an input via sensory systems. And then there's a serial cognition step in there, which would be in behaviorism, the black box. And then there's an output via motor systems. And you think that is not that modern approach is not the correct way to think of the brain either.
No. Let me ask you, though. Do you agree that people describe it that way?
I think that...
it's tough to pin down. It's kind of tough to pin people down.
It's really tough to pin down, and there's the risk that you're attacking a straw man in that case. So in a sense, it's at least it frames the problem very well. And I also think that this is a dynamic thing. So I think that the ethologists are having their day right now, right? So this is, and you probably helped bring this back into the fore. Yuri Buzaki just wrote a book, that brings this idea in, and everyone's talking about Tolman and all of the old great behavioral studies and all this. So I'm not sure what the main approach is, the way that people see this.
I actually think it has a lot to do with the words we use. That when people ask questions about behavior, right away they start using words like perception, memory, decision, action, etc. And I think that language is actually much older than any of these things we're talking about. That language goes back to, the Greeks at least, right? Yeah. Which of course assumed dualism right away. And I think it's because we're sort of forced to use the language that we have to describe behavior, and that language has phrases like, how do we perceive the world, right? Right away, you say, okay, how do we perceive the world? There's a we that's perceiving through some kind of a lens or something.
And there's the world that needs to be perceived.
And then there's the world that needs to be perceived. And there's some kind of transformation between this very noisy, kind of bizarre multisensory input into something that we are then later seeing, right?
Yeah.
And who is the we exactly, because it sounds very much like a homunculus. And of course, nobody really believes in that. But yet the way that things are phrased, the way the questions are asked, look at the psychology textbook and see how the chapters are organized, right? That already, I think, this reveals these distinctions that we make in studying the brain and how we then define ourselves as scientists. I am a motor scientist, and so I study this piece that starts with the command coming down from the cognitive system. That's a lot of people kind of, at least they talk as though they believe it. Although I think, again, like I said, I asked you, do you think that people really think that? I'm not sure people really take it that literally, but then when they design their experiments and ask their questions.
I agree with you that I think it's a problem with language. So for instance, now I'm very conscious about it because delving, deeper into your work, but when I invite people onto the show, I tell them a little bit about myself. I did decision making in non-human primates. And now I'm like, well, damn, decision making is not a thing. So I have to rephrase this, right? But then I've been thinking a lot about language lately and how we're really constrained by it. But, so on the one hand, people cite language as the pinnacle of our cognitive abilities. And that, of course, it's given rise to communication. And we, because of language, we know what Aristotle thought, right?
Yeah.
Much to his chagrin, I guess. But at the same time, it's like you have this word. So there's this concept, and, this is way off track, but we'll get through it. So there's this concept where you don't know what you're actually thinking until you can formulate it in language, right? Mm. But I don't think it ends there, because you have these amorphous thoughts, you get something down on the page, and then you actually reformulate your thinking based on what's on the page then, or on the screen, or wherever you've written. And so it's not like you've externalized your thoughts. It's like you have collapsed your thoughts into a bastardized form called language, and then you look at the language, and then you reformulate it based on what you think those words think, and it's this vicious cycle that.
Yeah, I think so. I think that's it exactly. I mean, I think what we have, our language. I think our language is the pinnacle of our abilities and our intelligence. It makes so much of what we do possible, but it has certain constraints. And one of them is we need definitions, right? And before we can convey anything to each other, we have to have an agreed upon definition of what the words actually mean, right? And so we have to define things. And because we need to formalize those sort of, ambiguous thoughts, as you're saying, into a, something on a page or something, we have to define the words we're going to use to describe the things that are in our head, right? And that's fine, right? But definitions are necessary, but they also right away constrain our thinking. And this is something Ernst Mayr talked about. He was a biologist, an evolutionary biologist, and he described this as typological versus population thinking. And he said typological thinking is when you define things in terms of types. And so there is something that's called a frog, and something else that's called a fish, etc. And we build definitions of things we see around the world, a tree, a mountain, right? But he suggested that that's potentially misleading for understanding biology, because what he favors or argues for is population thinking, where you think about distributions within populations and ask yourself why would there be something that you would call, a frog as opposed to a fish? And he says that there are reasons, right? And the reasons are historical. Where did that animal come from? In the case of biology, you can actually define, there was a population, the population split, and one part of that population evolved one way, one evolved another way. Now you have a distinction that's meaningful, right? The distinctions themselves emerge from this historical process of evolution, right? And it sort of makes sense to talk about types, but don't forget where they came from, right? And that's kind of one of the things that I've always struggled with is, when, it's like, if you need definitions to ask your question and then do your experiment, well, then you better be sure you've got a good definition to start with, or you have very little hope of getting an answer that's actually relevant to what you're trying to understand, right? And so what I'm saying is that we have our definitions, many of which come from our language and from sort of pre-scientific ideas how to talk about behavior. There's, how do we perceive the world? How do we remember and store and recall memories? And that's a convenient way to describe to ourselves what it is we're talking about, what it is we're interested in. But reality, biological reality, I think is more like Mayer's population thinking, that there are systems that have some shared history and some different history. And the difference is why it's meaningful to discuss different species or different aspects of the brain. But again, not forgetting that they have some shared history. And so I think this is why I'm so focused on evolution, because I think it tells us what the real types really are, what the underlying sort of ontology is that we then use our words to ask questions about. And so I think if we know the history, we'll have a better idea on what the right definitions are, and then we know what better questions to ask.
So this is a really admirable approach to me, because I was going to say no one can agree on definitions anyway. And so one tract then would be to go off and do some philosophy and talk about, well, how do we need to define these things? And a separate tract, which is what you're taking, and we'll get into it in just a second, is to say, well, we can actually define things better by looking through evolution. All right, so let's go ahead and just get into your phylogenetic refinement approach. So I think it's one thing to appreciate evolution as a neuroscientist, which all of us do to some degree.
Sure.
But it's almost like paying lip service, I mean, it's another to connect evolution to minds and to brains, and especially to try to connect all the dots from the first organisms, behaving organisms, all the way to us little old humans and our brains.
Yeah.
What would be really hard is to write a book about that. Do you know anything about that?
Well, I'm working on one, yeah.
I know you're working on one.
Yeah. But there's actually quite a few of them. There's actually a few books that do connect, written by real experts in evolution. And the one I'm reading now is actually, I would say, the best one.
Oh, I was going to ask you which one you'd recommend of all of these.
Well, I would highly recommend Northcutt and Streiter, or Streeter. I'm not sure how to pronounce the name. Glenn Northcutt is like the grandfather of evolutionary studies among vertebrates and invertebrates, one of the major figures in the field. And Georg Streeter is one of his students. And the two together wrote a book that just came out this January. And I've been waiting for it for a long time, and I'm reading it, and it's fantastic.
What's it called?
Now, it's called Brains Through Time. So this I'm just reading it now, and I'm getting a lot out of it. I mean, I knew a lot of the material that they cover already, but there's a lot more in there that's now there is. It's a little bit like mine in that it's chronological. They start really with early vertebrates, and they get to primates essentially. And it's excellent because it's really two of the world's experts.
Yeah.
So they really know what they're talking about. However, that doesn't mean that they represent what everybody agrees to be the case.
Okay.
They still represent views, and there's still debates, and some of those debates are really important. And so I'm struggling with deciding where I stand on some of those debates. But that's for later. But anyway, that's an excellent book. Another person I would highly recommend for someone like you is Steve Wise's books. Mm-hmm. Now, you know Steve Wise from his neurophysiological work, but he has in recent years started writing books about evolution. And they are, there was one in 2012 with Richard Passingham on the frontal cortex, which was fantastic. Another one with Betsy Murray and Kim Graham on memory, which is also fantastic.
Okay.
There's another one he's working now on. There's at least two more that he's working on now that I would again recommend, even though I haven't seen them yet. So there's some good books out there that are quite good. There's some more philosophical books like Mallet and Feinberg about the origins of consciousness. Mallet is one of the world's experts on evolution, and Feinberg is a philosopher, and they teamed up to write this book. And it's rather good. I disagree with some of it, but the evolution material in there is excellent. So there is a lot out there. Mine is going to be much more for computational neuroscientists, sort of. So the kinds of things that we're interested in, theoretical neuroscience and much more speculative than certainly the Northcutt and Streeter book, which is very serious, solid stuff, solid evolutionary material. Mine's going to be much more speculative about what I think might have been the functional reasons for certain things.
But it still has to be grounded in all the serious stuff. And I know you...
Oh, yeah. Well, I'm reading all the serious stuff, so...
You have to get through that. I mean, it is a slog. You're doing some good work there. How long have you been working on this book, and how many more years?
Well, I started in 2016 when I did a sabbatical. I just said, I'm going to finally start writing this book that I wanted to write. And essentially what most of my time is not writing. It's reading. It's reading all these papers.
Sure.
So I spent, that summer I spent reading about the Amphioxus, which is a very key animal. Yeah. And then fall was all about lamprey and Sven Grillner's work. And so I'm I'm doing my reading chronologically also. Chronologically in terms of, what evolved, what were the earlier stages, because before I can really have good ideas about later stages, I need to know what the earlier stages were. So
right.
I'm building my knowledge. I'm sort of working my way back up to monkeys slowly. And currently I've started reading about really amniotes, so birds, reptiles, and mammals. So I'm still got a long way to go.
Yeah,
it's going to be a long slog. But, at the same time, I'm running a neuroscience lab and teaching.
I know.
Can't spend that much time with it.
I was just reading about sponge neurons the other day, and I was thinking of you, and I was thinking, gosh, how does he, if you're going to do this, like, how do you stay focused and energized about it through all of these steps? So let's back up real quick. Let's talk about what you're doing and sort of what your approach is. So you call it the phylogenetic refinement approach. So what is that?
The idea is essentially it's almost like you have a model of a very ancient system, which in my mind is a basic feedback control system that's essentially doing homeostasis. And then you gradually refine your model, but you refine it in a way that respects the phylogenetic sequence along the lineage that interests you, right? So I'm interested in the human lineage, right? And for that reason, for example, I almost read nothing about cephalopods and octopi, etc., right? They're super cool. Don't get me wrong. They're amazing animals, but they don't tell us about our lineage because they split off so long ago,
right,
at a time that our ancestors were nothing like humans or octopi, or they were essentially bilaterally symmetric worms that sort of moved along the ground. They did nothing like what we do or octopuses do. Anyway, so I'm focusing very much on the human lineage, and I'm focusing on essentially just gradually changing it. So, gradually modifying that model. So simple homeostatic system that's just sort of, wiggling around on the ocean floor, following gradients, etc. How does it gradually develop certain kinds of distinctions? And one which is, I think, very important is staying put versus going somewhere else, right? So if your current environment is pretty good, there's certain local behaviors that you want to engage in. And there's a sort of moving around and looking for local gradients of where nutrients might be, right? But if you start to deplete your environment, or your environment is just not that great to start with, then there's a very different type of thing you need to do, which is go somewhere else.
Yeah.
More long range. And that requires a very different kind of system. And I think this was one of these early distinctions that developed in what became the forebrain, but at that time it was mostly hypothalamus. And anyway, and so then you gradually develop a distinction of systems specialized for the local behavior versus the long range behavior, and then you sort of follow how each of those might have developed over time to deal with their needs. And again, always taking an existing system and trying to describe how it might have been differentiated and elaborated in a way that actually respects what we know about what happened, what change just happened in the brain at that time.
That's a big key too, is to know the behavior, to know something about the behavior, to be able to tie it into brain development and to make any sort of confident statement about how these things are manifesting.
Well, like I said, it's a pretty speculative book, so it's not going to be that confident, right?
That's fun. That's fun, though. I like that.
It's fun. Well, it's fun. And I guess there is a lot of data on this, though. There is a lot of people have really thought about these things a lot. And they're not people that, you and I will come across when we read basic neuroscience. There's a whole field of comparative anatomy, comparative physiology that people have been thinking about these things. What did these animals do? And there's a lot of inference. And so, for example, the Amphioxus is a very key animal because it split up from us so long ago, and yet it has some of the basic organization of our nervous system. And there have been, people who have studied that animal in quite some depth. And in particular, Thurston Lacali has studied the anatomy of these animals and did essentially a lot of what I would like to see speculated about. What were they capable of? What kind of behaviors did they do? How much of the current behavior of Amphioxus actually reflects the behavior of the common ancestor we share with that animal? And that's a pretty good animal because there's good reason to believe that it didn't change so much. Lamprey they didn't change so much since we diverged.
But that's an interesting thing too, because the environment changed, and thus, even if they have the same system, their behaviors are going to be likely different and using the system to do different things, no?
Well, there's good evidence that Amphioxus essentially, at least for the last 350 million years, hasn't changed its behavior much, in part because of fossil evidence, and not just the bodies, but their, how they're found in, the burying behavior, et cetera. And of course, there's a lot of gaps in this, but again, there's a whole field of people studying this. Lamprey are another good example of an animal that has, invaded a certain niche that it looks like they've remained in successfully without dramatic changes, at least. So, sharks are a great example.
Sure.
Once you eat everything, you're set. You stick with that strategy. So I think, people studying, for example, Grillner studies lamprey exactly for this reason, because I think he's right. They represent pretty well what our common ancestor was. Now, of course, they've split off from us about 550 million years ago by some estimates. Now, of course, they've been evolving all that time too, but they haven't gone through so many niches. They haven't gone out on land and whatever. It's not like birds that have gone through many niches. Mm-hmm. So lamprey tell us a lot about our common ancestor. Of course, there is still a lot of gaps. Right?
Yeah. The gaps are infinite. I mean, this is, did you realize what you'd be getting into when you thought, I realize now I need to study evolution?
Well, I pretty much knew that it would be challenging. One of the things that I was very excited about pretty early on is when I realized that just how much knowledge is out there, how many people have been working on these kinds of questions, and how, at least to me, good their findings are, how strong their findings are. And there's essentially I've sort of picked a few experts whose work I just believe, based on mostly I see how their field responds to them and the methods they use.
Yeah.
And so for one person in particular is Luis Puelles, who is a developmental neuroscientist who studies fate maps in development. And he has developed a model of the brain, which is really very different than what we have in our textbooks. But I think it's fantastic. And I think it will become our textbooks, in 10 years if things go well. And his model, he's a controversial character. But I've talked to the people that vehemently disagree with many of his ideas, and yet they still, I think, believe that his methods and the backbone of his model is correct and is important to know, etc. And it puts things into place. One of the things that's good about it is because it looks at development, he can apply it to many species. So he can do it on the lamprey. He can do the fate maps on the Amphioxus. He can do it on mice, which is what most of his work is. And when I say he, I mean he and people in his group and in the field that he's in. And so they can come up with essentially a developmental strategy for deciding what's homologous to what, whether this part of this animal's brain is actually related to this part of this other animal's brain, even if they are hundreds of millions of years apart in evolution. And that provides a kind of a map that you can now have. And it applies at least back to the Amphioxus. And then there's other people like Detlev Arendt who will connect from really early multicellular animals up to the Amphioxus. So there is actually a continuous body of work that will link all the way from early living multicellular animals all the way to our lineage, because the Puelles model will apply to all vertebrates. And it's growing data, and it's data that's, I think, helped by all the modern techniques, like genetic techniques. Mm-hmm. So I think it's actually extremely promising. I kind of feel like, I'll write my book, And then when I finish it, which will probably be a long time from now, I will decide that I should start again because, there'll be some better data.
That's the problem. So doesn't Steve Wise puts them out every few years, right? That's what you got to do, man.
I know, but again, if I do that, then what will happen to my students and the rest of my life?
Right.
So in a sense, though, yeah, I mean, I have to do a lot of revising, but it's okay. Again, it's the reading that takes the time. The writing is not such a big deal. Yeah. I mean, it's a job, but it's the reading it's the reading and deciding what next to read and what next to conclude. Anyway, but the point is, so with some of that, I can come back to this issue of definitions. That if you have let's say you have the Puellas model comparing how the different brain segments appeared in evolution by inferring common ancestors from comparative work and embryological work. Now you have a kind of a guideline to say, well, this distinction is old. The distinction between the hindbrain and the rest of the brain is very old. That's a very fundamental distinction. Then there was a distinction between the forebrain or the prosencephalon and what you might say is the midbrain, but it actually includes the dorsal thalamus, according to a paper that came out about a year ago. Very strong data suggesting that the thalamus is part of the same basic segment as the superior colliculus. That's the dorsal thalamus, whereas the ventral thalamus and hypothalamus are the front of the brain. Yeah. Right? But one of the things that I didn't realize, which is apparently very well established, is that the whole cerebral cortex, basal ganglia, amygdala, hippocampus, all of those things are a bulge out of the second segment of the hypothalamus.
Which started all the regulation, I guess.
Exactly. It makes perfect sense, right? If hypothalamus was essentially the top-level regulatory controller of physiology and, hormonal excretions and neuronal commands, it makes perfect sense. It's still strongly involved in all those things. There's all kinds of motor signals coming out of there. And it's just one part of it that sort of mushroomed out and exploded in vertebrates in the telencephalon.
It makes perfect sense if you take your, I don't know if I should say philosophical, your approach to what the brain's function is. Yeah. And maybe this is a good time for us to sort of just get all the cards on the table and, bring it back to going from 0 to 1, from before an organism to after. So your papers, first of all, of course, I'm going to link, to many of them, but they lay out this really nice story of, before there was an organism, and then there was an organism, and what that organism needs, and how those needs are met. And I don't know, I'm describing this, but I should just let you describe your approach to what the brain is and why it is the way it is.
Well, so there I'm essentially just, sort of repeating what certain people have said about the origins of life and the origins of behavior. And the origins of life, to my understanding, fairly well established. It has to do with autocatalytic sets. So, and Stuart Kaufman had a very interesting, I think, argument in favor of this, which, as far as I can tell, is fairly well accepted, is that if you have chemical reactions and you think of them as a catalytic reactions like an arc and the chemical is like a node, if the system expands such that the number of arcs expands faster than the number of nodes, at some point, it's simply inevitable that you'll get closed loops, where you have catalysis that self-reinforces itself in a loop. Now, that doesn't mean it's going to, launch life immediately, but it is one of those sort of things that's kind of inevitable in any sufficiently rich chemical environment. And I think they call it percolation theory or something, where at some point it just sort of creates these things. And at some point, these things will become self-sustaining. There's a lot of work on this. Eigen and Schuster and Matrana and Varela, who are neuroscientists, actually wrote a book called Autopoiesis, is that life starts with things that sustain themselves.
Is that the 1991 book?
Was it 91 or was it earlier?
I don't know.
I think it might have been earlier. Anyway, so the point is that once you have a system that sustains itself, you have metabolism. All right. And, obviously, a lot of the physiological processes are essentially feedback control, homeostasis, it's not really stasis, but but it's a system that self-maintains itself. Now, going from that to behavior is a big step in a sense, but functionally, behavior is just a feedback control circuit that extends beyond the organism. And what I mean by that, because you've read the paper, is just that if you think of the interactions, like if you can't control your internal physiology because you can't make a certain nutrient that you need, that you have to absorb it. If it's out there in the world and you're not close to it, well, moving is a way of controlling your state, because now you're likely to move yourself to a place where there's more of that nutrient and you can absorb it. And so the strategy of having a kind of the more you need something, the more you move around, is an extremely common strategy that single cell animals do and all kinds of animals do. There's a pattern that emerges extremely often called a levee flight, which means you make a certain number of small movements, and every once in a while you make a large move. And it's a very good way. It's a very good way of sort of covering a non-uniformly distributed environment. And there's a theory by Thomas Hills that suggests that regulation of that was an early role for dopamine in early animals. Mm-hmm. So if you're absorbing stuff a lot, you release a lot of dopamine, and it keeps your behavior local. Whereas if you're not absorbing stuff, then your dopamine levels drop, and now your behavior turns a little bit more global. So it's like regulating now based on reward rates, whether you stay local or whether you move further apart. And he cites evidence that again, this is an extremely widespread phenomenon many animals use. So, and that's a feedback control system. It's trying to control your essentially nutrient intake rate, a very simple form of foraging. So it's essentially it's a behavior that is extending the metabolic control that through the environment. And this is an old idea that dates back at least to John Dewey, but probably even before that. That behavior is a control process. John
Dewey was writing about the reflex arc when he wrote about this, right? So just to take a giant leap then, I mean, your premise then is that the history of evolution is essentially extending this control. I'm not quoting you well, but extending this control through evolutionary steps more and more outside, further and further into the world.
In more and more sophisticated ways. More sophisticated ways. And the systems in our bodies that are responsible for doing the control that extends past the body have become so elaborate because the problem is so endless, right? You can be a simple animal wiggling around on the ocean floor, but, you can do better by being a bit more elaborate, and it just never ends. I mean, your world is becoming more complex. The levels and abstractions that are out there for control of your state, predators, escape behavior is a type of control. If you face a threat, the thing to do is to eliminate that threat, either by fighting or fleeing or cowering. And again, the problem is so gigantic and so endlessly complicated that it's makes some sense that the part of the body and the brain that is responsible for that type of control. So, the hypothalamus has a terminal segment, what Puelas calls the terminal hypothalamus, and what Swanson calls the rostral hypothalamus, which deals mostly with things like temperature regulation, etc., and internal body physiology. That part has not changed so much, right? Whereas what Puelas calls the peduncular segment has grown a whole new telencephalon inside of it with a cerebral cortex and basal ganglia and amygdala and hippocampus, because what it deals with is that other kind of control that has to go through this incredibly complicated environment. And so it kind of fits that's the part that has become so elaborate in animals, in vertebrates already. It's already a very complicated system. I think you can think of behavior as in terms of control, and even communication. Even communication. The simplest types of communications are essentially attempts at persuading the animals around you to do the things you need. If you're a helpless baby, you can't produce the nutrients.
Oh, God.
You can't go out there and get the food, but you can cry. And the example I like to give is, it just so happens, now you have kids, right?
Yeah, oh yeah.
It just so happens that in their world, in their niche, there is this really convenient thing that if they cry, then there's this incredibly complicated creature who's willing to do anything to satisfy their needs.
Unless their dad is a sociopath like this guy.
Oh, yeah? Well, how are your kids doing?
They're great. They're great. I'm a decent father. But I did...
But as you know, it could be 3 a.m. and it could be minus 30 outside.
Yeah.
You're going to go to a convenience store. You're going to get in the car. You're going to do everything it takes to satisfy that need, right?
Sure. Yep.
So all they really need to do is cry, right? Now, that's, of course, simple, right? That's a simple control. And it works because they can rely on the fact that in their niche, there's this creature that will do this. If there wasn't, that's it. They're dead, right? So their strategy is to rely on the presence of a parent. And that's a very simple type of communication. But over time, you will teach them, mostly by your behavior, a more fine-tuned way of controlling you. It's, I'm hungry or I'm thirsty. I want that toy. There's lots of ways you're going to do the harder job actually of training them to notice these regularities in your behavior. You're going to make them obvious. You're wired to do this essentially. And now they're able to control you in much more sophisticated ways.
Yeah.
And of course it keeps going from there. Now, I'm not going to try to explain really, really higher cognitive behavior, like, right now we're exchanging information. I'm not really trying to control you, but I am trying to persuade you at least.
Sure. Yeah.
I'm trying to persuade you to think of things the way I would like people to think in order to, work together on these kinds of questions. So communication, I think, started as another extension now through other creatures. And, again, became very sophisticated because of in large part because of the other creatures.
But the central idea that keeps recurring in all of these, in basically any, I'm going to say cognitive function, although I know that that's a terrible phrase could be construed as a terrible phrase in your language these days. But, if you give some sort of function, well, let's say language is just, you can look at it through the lens of it being a control mechanism and controlling your environment, and everything that our brain is doing can be looked at through that lens. Is that?
Well, I think ultimately, yes, but I think that's not going to be enough to explain it all, right? Because there are things that we do where the immediate control aspect is really far removed, and all the intermediate steps become such a big part of it that, when I work to make money, so I have money in the bank so I can go buy food, you could say, well, I'm controlling my food intake, right? But it's not really a full explanation of the things that I do. Why do I derive pleasure from one type of work but not another type of work? I mean, there's just levels and levels of complexity that go beyond simply the fundamental control aspect. And I think those are interesting, and I think they call for very specific theories that are not about levee walks or simple animals.
Sure.
Half a billion years ago. But I still think they need that context. They need the context of the control system. And it has to do with semantics, that I think the semantics always come from within that control structure. I don't know if you want to get into that whole philosophical kind of worms, but
Let me just play devil's advocate for a second and see what your thoughts are. Two questions. Sure. One, do you think it's possible? I was thinking about adding control mechanisms on top of other control mechanisms as evolution slowly, stepwise, in very small increments, keeps adding on and adding on. So first question is, do you think it's, possible that there could have been an evolutionary emergent, quote unquote, leap, such that, the complexity of our brain processing, it is, goes through like sort of a phase transition, right? So that there are meaningful properties at this emergent level, so it becomes insufficient to attend to the nervous system evolution, right? Or think at the level of a feedback control process, sort of like you were just saying, but where it actually wouldn't be informative to look at all the little steps because at some point there was a phase transition and now we have a different monster. Does that sound ridiculous?
You mean, have we moved beyond the simple control type system to create a new domain sort of behavior?
Sure.
A new type of behavior. I think yes, but not entirely. And again, it has to do with meaning. So I don't think our brains have changed so dramatically, from at least our primate cousins. Primates do a lot of very sophisticated things, and they include some of the important elements that we build upon so much more, like social interactions and communication. It becomes so important to primates that that's sort of one of their strategies. Mm-hmm. One of their major strategies is social groups, and social groups create their own domain of needs and demands and threats. So in humans, though, we took a particular aspect of it, which is linguistic communication, I think, to a level far beyond what any other animal does. And it's been extremely successful. I think it has to do with the abstraction aspect. Again, with the definitions, the fact that we communicate in a way that's somewhat symbolic, that gives us an ability to convey information, convey knowledge in compact ways. Now, it's not completely absent from the animal world. I mean, bees' dances have certain symbolism to them as well. But in our case, it's just so far beyond that it becomes a very sophisticated system. And I think it, again, has to do with child development, that we have a brain that's sophisticated, and it's very much specialized for language. There's a lot of resources poured into in our evolutionary lineage, essentially, that allow us to have language. The changes in our throat, the changes in our brain, etc.
Right.
And so, early cavemen whose brains were essentially like ours, had these complex social groups, right? But and they behaved in sophisticated ways. But what happened, I think, is that because every child is guided essentially into a more and more sophisticated world. Every generation is teaching its children a more sophisticated world of abstraction with more and more meanings piled upon more and more meanings. That it's a little bit, I've heard the analogy with autocatalysis again, that as the number of different interactions grows faster than the number of nodes, you have this thing which ignites and creates this incredibly rich domain of interaction. And so I think what we have is, so let me get back to meaning. So I think meaning is very difficult to account for in the computer metaphor, right? This is the well-known symbol grounding problem, the Chinese room argument. AI had called it the framing problem. This was sort of the reason why classical AI never accomplished true general intelligence, is because the meaning was absent. There are, of course, other things as well, but I think that's clearly one of the major things that was missing. And I think in terms of a control system, meaning is trivial. Meaning is always there. If you're interacting to control a variable, then the meaning of the things you interact with and the reasons for your actions, it's all relatively straightforward to understand where the meaning is.
It's tied into the value of the things that you're interacting with.
Exactly.
Right?
Exactly. How is it that it helps you accomplish what you're trying to accomplish? So objects have meaning because they afford certain actions. Some bring you food, some give you shelter, etc.
And in that sense, just to pause there, in that sense, they don't have some sort of ontological meaning independent of your interaction with them.
Right. The meaning is to me. The meaning is what's in it for me. Okay. A certain type of object might have different meanings for different animals. A mouse, a hole is shelter. For a cat, the hole is food. Maybe mouse, food. Right. Anyway, so the point is that if you have an interacting system, it has meaning, and any representation along the way has meaning. But if your system now is the communication type of controller, which is extending through other creatures, and because of extensive sort of cultural norms that are established in a particular social group, there's increasingly abstracted symbolic things that are being conveyed, then they can have meaning. They have meaning because they still exist within the context of that control or exchange.
You can use them.
Interaction. You use them, exactly. There's a paper that I would suggest, which is by Giovanni Pazzullo and Castelfranchi, which is called the symbol detachment problem. They ask not how symbols get meaning, but how meaning detaches essentially into being symbolic.
You've written this is opposite of the way we normally conceive of this.
Exactly. But I think it's the right way to think about it. It's not that you somehow attach meaning to these representations that are being transmitted back and forth when we talk. We're interacting, and somehow within the context of our interaction, these things get clustered. These packets of information that it's not just me waving my arms and baring my teeth. It's me uttering a phrase, back off.
That means I'm waving my arms and uttering.
I'm waving my. It has come to be accepted as it's a way of accomplishing that same thing. And now I just say back off, and if it works, you'll back off.
You could say, "Oh no, you didn't." That's another way to do it.
Yeah. There's the point is that once you have these interactions established within a particular social group, now they have meaning because they stand in for all those things.
Right.
And so, you can have symbols emerging. It's still a long way from what we're doing now. I'm not saying this explains all human behavior, but come on.
Yeah. No, the idea of abstraction, I don't know. I feel multiple ways about this. Sometimes I believe that I have lost belief in nouns or as things, an abstract entity. When you abstract something, that doesn't mean it's a thing. It's still a process. It's still a cluster of processes going through the same formation, and then we can kind of abstract it. But I don't think that we're good with words doing that. And I think that we fool ourselves thinking that we have a good semantic understanding of what the abstract thing is. And this goes back to the computer metaphor, because I think that language, part of its job is to fool us into thinking that we do know what things are, and we're brought up communicating in language. And so our own introspection, which, as we know, is horrible relative to what's actually going on in our brain processing. Yeah. So our own introspection, we're culturally brought up to conceive of our minds as being the cognitive thing and being part of that computer input, cognition, motor output. So I think it's a really difficult concept to get rid of, because everything we do in culture seems to advocate it.
And again, I think it's why the psychology has gone the way it did, is because it's interested in the human behavior. It's interested in human intelligence, human communication, emotion, etc. But I wonder if, maybe we're not really ready to tackle those questions because we haven't phrased them correctly. I mean, I can't claim to have an answer to, why somebody writes sonnets or something, or composes music. But I think I don't have certainly any illusion that I'm going to see the answer of those kinds of questions in my lifetime. I understand why people are interested in them and want to study them, but I think you kind of we need more of a foundation in the brain, I think, before we can really address some of the things that we do. A lot of the brain was established long before humans could do any of those things. So obviously, it could be established for doing those things, right? So somehow we need to have an understanding of the foundations before we can talk about that. And language is one of them. I don't really know that much about language because, again, I'm doing my reading chronologically.
Chronologically, you're never going to get to language, man.
Well, fortunately, lots of other people have, already done these things. So yeah. I just have to find the right viewpoints, and it's not like I'm the only person doing this. So I just have to get to that point. My understanding right now is that there's a number of good, I think, well-justified theories that say that, language really changed us, or at least our abilities. It helped us do a lot of the things that we call cognitive. But it's recent. And I don't think it reorganized our brain entirely into being like a digital computer. I don't think that has changed at all. I think we've embellished a particular strategy of communication in a way that is incredibly impressive, but it shouldn't make us believe that that's the backbone of how the brain works. That's not how we should start neuroscience. I don't think we should start neuroscience with those kinds of questions.
Yeah. I mean, I see us as barely symbolic, language just is this latest sort of ability on top of all this other stuff that's been around and well honed over a long period of time, and language doesn't know how to use this stuff.
Yeah,
I think we're just barely getting by.
Yeah. Anyway, I don't know if I should say too much about language because it's really not something I know that much about. I have sort of deliberately focused on other things because of the attitude that I have that we need to know the foundations.
What do you think? So, I mean, in neuroscience, we're plagued by these imprecise definitions, and we use filler terms like representation, encoding, something encodes a representation. And it creates confusion. I feel like evolution has it even worse in some respects. We sneak teleological statements into things like saying, birds evolved wings because they needed to fly away from predators. What is something important about evolution that may be misunderstood or underappreciated, even in the scientific community, not just when I'm sitting around with my Christian relatives?
Well, I think that is certainly one, that we kind of think of evolution as providing answers to questions posed by the environment. I think Dawkins had that phrase that's not what evolution does. It's not, it finds solutions to a problem. It's really exploring variations, right? And it just so happens that some of those variations accomplish things that used to be a problem, right? And so it looks like progress is being made, right? But if you actually look at what happens in evolution of a particular lineage, by any measure of complexity or optimality or something, species go up and down all the time, right? What you really have is that you have a growth of diversity, but as you have a growth of diversity, it's kind of cropped at the lower end, right, of the really simple animals, because they won't make it. And so it looks like over evolutionary time, animals are becoming more complex, but that's just because as diversity grows, you can get further. That tail will get further into more complex animals. And I think the difficulty is of knowing why something evolved, right? That's an extremely difficult question to ask, and it's notoriously difficult. But we don't need to ask that right away, because if we look at the data that does exist, we can still say what happened, right? We don't know why maybe something happened, but we can tell what happened. We can tell when in our history certain distinctions emerged, between different brain systems? When did certain things get more elaborate? When did specializations that we can see now occur? So once we know those things, it changes what kinds of, for example, we can be pretty confident that evolution doesn't add structures on top of structures. There's this old idea in psychology, the triune brain, that's still very, very popular, that you add a sort of a mammalian brain on a reptilian brain, and then a neo-mammalian neocortex on top of that and become really sophisticated. But that's not at all how things happen. These structures are actually very old. And what you see is a progressive differentiation and specialization. And we know what happened, but it's very difficult to say why. You know, sometimes it's just dumb luck, right? I mean, sometimes an asteroid falls from the sky and blocks out the sun, and animals that, by all accounts, should have been successful suddenly die out in large numbers. And so these things happen, but we know what happened, right? So it's like we can look back at evolution and we can interpret what actually happened, and then knowing what, let's say, hippocampus does in animals, in current animals, we can make, I think, fairly well-informed hypotheses as to why a distinction emerged in early vertebrates between the thing that became the hippocampus and the thing that did not. And I think it has to do with exploration. Again, it's that stay put versus go somewhere else distinction. Hippocampus became the thing that will get you somewhere else. And so you can, with the picture of evolution that can be relatively well established, I think you have a better sort of roadmap for where to speculate, right? It's still going to be speculative, but you're speculating with a fairly solid data set and a fairly, I think, sensible set of constraints that tell you what are the speculations that are just ridiculous and which ones are more promising. And that maybe can actually make predictions.
You contrast this approach, looking back, the phylogenetic refinement approach, with our current, or many of our current approaches, which is a more engineering looking forward approach and defining the problem. And there's a problem in that. What's the problem in our engineering approach in defining the problem and solving it?
Well, because again, we don't know whether we've defined the problem correctly. So for example, perception, okay? From an engineering standpoint, you might say, I want to build a system that builds an internal representation of the external world, right? And that definition of the problem might motivate you to build something that has a kind of Mar-like labeled model of objects in the world that have particular labels attached to them, etc. But when you look at the brain, it doesn't seem to be organized that way. The what and where pathways are quite divergent. They have very different properties. Sometimes they duplicate things. The superior colliculus does some of the same things that the parietal cortex does, but differently. And why? And it's kind of hard to interpret. Why would evolution solve this problem this way? And the answer is, it wasn't solving this problem. It was solving a very different set of problems that gradually changed over time. And if we think about what those problems might have been, then it might make more sense. This idea of affordances, for example, right? If you're going to interact with the world, you want to interact in ways that suits you. And so you need to be sensitive to the things in the world that you can exploit to serve you, like, a shelter or food. And if you have a system that's able to guide itself in the world, then it makes good sense, actually, to have a system that's specialized for the spatial guidance and another system that's specialized for saying, well, the thing you're pointing at to right now is not that great. Go point at something else, And it makes sense for an early animal to do that, because that early animal was not interested in understanding the world. It just needed to get some food as fast as possible and escape from predators as fast as possible, etc. And so the problem it was solving is actually a different problem. The binding problem is a good one, right? How do you bind information from different modalities, etc.? And in some ways, it's not really a problem for a simple animal interacting in the world, right? If it has its receptors that are wired up to the things that, let's say, determine attractive versus repulsive objects. And if those receptors happen to be facing forward, then the decision you have to make is the thing I'm facing forward, the thing I want to approach, or do I want to turn, right? And if another system is just saying, yes, I received the approach command, or yes, I know I just received the turn command, then that can be the one that guides you in space, and so on. So in other words, binding the what and where can be done actually through space, essentially, spatial selectivity.
Through controlling it, your action.
Yeah, exactly.
Well, it might help to state what the affordance competition hypothesis is.
Yeah, so this was an idea that again, it has actually a long history. I call it that because I want to emphasize the affordance aspect of it, that Gibson described as one of the sort of fundamental aspects of perception, is to perceive what things in the world afford you in terms of things like shelter, food, mates, etc.
And by the way, is that still a good book? Would you recommend that book?
Gibson's book?
Yep.
Absolutely. Yeah,
okay.
Absolutely.
Okay.
I mean, I think, you'll get a lot more than just that out of it.
Okay.
And there are some things about Gibson that I might not agree with. He went fairly radically in the non-representational view, which I wouldn't be quite as radical as he.
Maybe I need a Cisek annotated version then.
Or Pizzulo. I mean, many people, but I think that idea, is very important. I think people recognize that more and more. The idea that affordances are there. And it's just like a fact of physics, almost. If you're an animal of a certain size, a certain thing will afford shelter for you, right? Yep. And so if you're that animal and if you're faced with a threat, well, it would be very useful to make use of that, right? And so the affordance competition hypothesis is essentially just saying, well, maybe what really happens, so it's kind of a theory about decision making, but it's not the kind of decisions a lot of people want to study, like, economic formal decisions about like what career to choose. It's more like if you're running around in the world, do you run through this or run in this direction? Behavior
is what I mean.
It's very much about behavior. And the idea is that, and it's based on all these findings that the variables pertinent to selecting actions are in the system that seems to be guiding those actions. Now, those ideas are out there. And so this hypothesis is just saying, well, maybe the parietal cortex is doing the sort of sensory motor control, but presenting or at least processing in some way multiple affordances at a time. And other parts of the brain are helping to select between them, because you can't run in two directions at once. You can't interact with that many objects all at once. So another system, namely the ventral stream, might be specialized for helping you solve that selection problem. Now, that idea was essentially based by my desire to look at some of these ethological problems, real-time behavior problems, in the context of neuroscience. But I mean, I think, I'm revising many aspects of that idea simply because I see that it was extremely corticocentric. This was about the primate neocortex, right?
Yeah.
But the questions that it deals with are much more fundamental. And they were things that animals were dealing with long before that structure even existed, et cetera. And people have talked about this. I mean, the ethologists have talked about these things in terms of tactile systems, mostly, for dealing with the affordances in the world, orienting you around, et cetera. Hypothalamic system for selection and things like that. So there's a lot more to it than neocortex, I think, and it's kind of a primate cortical neurophysiologist's view of something that's actually much bigger.
Yeah.
So that's in some revision in a sense. And again, I don't know if you know Graziano's work. Michael Graziano, I think, changed my way of thinking a lot.
With the body schema stuff or the latest consciousness stuff?
Not the consciousness stuff, the body schema, the action maps idea, which has been very well supported actually by other labs now and many other species. So that seems to be at least among mammals, questionable whether it appears elsewhere, but people haven't looked yet. But that seems to be pretty fundamental among mammals. And, tectum of the lamprey as well. So the tectum does action map, there's good evidence for action maps there. So, but the basic idea again is that the affordances are out there, the needs determine which one you should engage in, which potential actions you should engage in at a given time, because you can't do everything at once.
Does the whole control approach and Graziano's body schema, do they accommodate embodied cognition? I mean, they're all kind of wrapped up, aren't they?
I think so. I think they do. But there's two kinds of embodied cognition. There's the very radical embodied cognition, which is closer really to where I am.
Oh, okay.
Because embodied cognition is a lot like, it's still like cognition. At least a lot of the work that calls itself embodied cognition is still very cognitive. It's just using the body as another representational medium, or another way of gathering information, etc. But there's a way of saying that the embodiment is there long before the cognition, which is what I think. Mm-hmm. The embodiment aspects, the control aspect, the sensory motor control, was the foundation within which some things started emerging and creating things like symbols, etc. I mean, Piaget said this like 70 years ago, right? Piaget said all this in the context of child development. Again, at first it's all about sensory motor interactions, action perception cycles, and then gradually you build some kind of knowledge around it. Of course, Piaget is impossible to understand because of the way he writes. So I'm taking it mostly from other people's translation of those ideas.
And then gradually you control your parents.
Yeah, that's it. No, it's something like that. I mean, there was a very good book by this guy called Hendricks Jansen, that laid this out quite well, I think.
Catching yourself in the act.
Yeah, that's one. Have you read it?
No, I started. I've read the preface now, but I love these books. That's why I was going to ask you, like, which one people should start with, because throughout your work, you reference a lot of these older works: Piaget, Gibson, the Hendricks Jansen book, and all the ones that you've mentioned. And I thought, Jesus, which one do I start with?
Yeah, I don't know. It is a lot of stuff. I mean, the Hendricks Jansen book is brilliant, but it's discouraging because he does such an effective critique of almost all ideas that you feel like in the end it's like, okay, well,
nothing is left.
Nothing is left. But I mean, but I don't think that's really the case. I mean, I doubt he would agree that that's the case. But it just kind of came across, at least when I read it, it's like, oh my God, turns out everybody's wrong. But he's very much in favor of Gibson and a lot of these ideas, and very much, again, focusing on evolution as a key to tell us how to go about breaking up this big problem.
I think a lot of people, when they read your account, at least I'm speaking for myself, I immediately start to think higher level cognition things. How do I apply this thought process to consciousness? How do I apply it to attention? Whatever it is we call attention, which I know that we could talk about attention because we don't know what attention is. And, we could go down that road. But basically, like, people, I think, read this and think, how can I use this in my current project to reform the question in the right way? And I'll give you an example of a train of thought that I recently had, just being colored by reading your work. So there's the psychology and neuroscience of categorizing perceived stimuli. And there are different models, right? There's an exemplar model where you store all of the examples and then you compare, you get a new example and you compare it with all the stored models. And then I thought, okay, well, that seems inefficient. How do you compare it with everything? Like, is there a better way? Well, a more efficient way to do it is to use some heuristic rather than compare all the examples. And so then I thought, okay, you get an example and it sets off some sort of template matching via some Hopfield-like associative network, with some stored examples. And this sets off this kind of chain reaction or reverberation among other networks and other examples and on and on. But then some heuristic is needed because you can't just perseverate forever to decide when to stop and a stopping rule essentially, and decide when to take action, because action is the most important thing. So in this example, the idea of the primacy of action, leads to the idea of a heuristic or a stopping rule that sweeps through. It's its own mechanism, sort of, that sweeps through, I guess, and says, okay, it's time to move on. What have you come up with? What are the votes here? And then I immediately thought, oh, is this how you came up with the urgency model?
Well, yeah, not really. But I guess you could say that, time is running out and you should get on with it. Even if you make the wrong choice, you have to make a choice or
you have to move
by default. Yeah. Right. Well, yes, in a sense, it kind of fits with that. It's not really where it came from. It came more from the data actually, because I was forced to abandon the more classical evidence accumulation model just because we had data that just,
right.
We tried for a year and we couldn't come up with a way to make them agree. So, but it's true though, I think you are correct that there, in a sense, having such a thing is a necessary sort of mechanism to snap you out of it, out of excessive, sort of self-reflection while somebody else takes the food,
Right.
So yeah, I think in a sense that this sense of urgency, the time pressure, et cetera, is something that animals always have to deal with. And it would make sense for it to be a relatively fundamental, mechanism. But to the bigger question you ask is how do you apply, I have a certain attitude about picking the kinds of problems I want to study and I want to try to understand.
Yeah.
And it fits problems. If you're interested in sensory motor control and action selection, then it fits really well. But if you're interested in really more abstract knowledge, then I don't know what I can tell you really, except, that I'm sorry you might be asking the wrong question, or you may be asking in a way which is not going to be so helpful. And I think, here's attention's a good example here, I think, because attention from the sort of classical information processing view is a very specific thing. Now, of course, people have always been using the word to mean multiple things, but one type of attention is this idea of a filter, that because you're so overwhelmed with information, you need to limit it some way so you can handle it all. And so you attend only to a couple of things at a time simply because of a kind of a processing bottleneck, right? And for that reason, you have this mechanism called attention, and there's a network that takes care of this problem for you.
This is kind of from the information processing.
Yeah. This is from the information processing view, right? But if you actually look at the data, it's a mess. And, I'm not an attention researcher, but we recently wrote a paper, which I guess you saw, with a number of people who do study attention quite seriously. And this, we happened to be at a conference, where we were presenting sort of compatible ideas. And we decided to write a paper together where it's actually remarkable. We have six senior authors all together and were able to agree.
Whoa.
Yeah, that's quite amazing. At least for the most part, we agreed. Anyway, and the thing is that it's not a useful term to start with, in a sense, the idea of there's this thing called attention, and let's go look at the attentional phenomena and try to explain them in terms of an attention system. There's a long and well-known difficulty with doing that. In fact, since the beginning, apparently I learned that since William James' famous "everyone knows what attention is" statement, people have always been saying, no, it's a mess.
Oh, is that right?
But the point is, so we took I injected into this the evolutionary view, which is that, this comes back to the parietal cortex, right? So, the intention-attention debate in the parietal cortex, which has been going on for 40 years or so. It's hard to interpret this region. And why is it that attention seems to involve certain regions like the FEF and LIP, etc. We took the sort of Graziano viewpoint in a phylogenetic context of, suppose you have animals that have a certain behavioral repertoire. It involves things like jumping from branch to branch, sitting down and manipulating nuts or something. They orienting around, looking around. They have a phobia, which not all animals, of course, do. So they have these systems that control different aspects of their behavior. And one of them is orienting gaze, right? Now, because all of these systems that these animals really embellished, of course, I'm talking about primates living in trees, they rely very highly on vision, right? and they have a phobia. And because of the fact that they have a phobia and the vision is so important for all these things that they do, the direction of gaze takes on a kind of executive role, right? Once you have a system, and it's just one of their behavioral subsystems, right? It's the gaze. If you decide you're going to be looking around, it now takes on a kind of executive role. It's now deciding where to gaze, is deciding what information is available for anything that you want to do, whether it's jumping from branch to branch or baring your teeth and raising your arms at a opponent. And so the thing that happens in primate parietal cortex is that the system that happens to be responsible for controlling gaze takes on all these roles that seem to be attentional, that it now drives so much of decisions, etc., and becomes kind of a calling the shots, kind of a leader for the rest of the behavior. And so for that reason, there happens to be this system in the brain that behaves this way, but it's completely different than other types of attention, like, auditory attention to the fact that if you're listening for a certain phrase in a particular conversation, you'll hear it more readily, or attending to a certain part of your body or something like that. It's not because of a computational bottleneck that we have it. It's more of a behavioral bottleneck. There's only a few things we can do, and a really good strategy for organizing our behavior, if you're a visual monkey with a phobia, is to gaze around at things, and it looks like what we call attention.
So there's not a central homuncular executive area that's controlling all this?
No, not really. Well, there's a particular circuit that is highly responsible for where our gaze goes, and that includes, of course, the superior colliculus, etc. And that system does what it does. It moves the eyes, moves gaze. It does an aspect, a behaviorally relevant function that looks like it's solving a computational bottleneck in a sense, but that's not its origins, right? Its origin has to do more with the fact that these animals happened to, that mammals got long necks and movable eyes earlier than that, and developed a phobia, and now became so highly visual, which they weren't before, right? They weren't when we were closer, like rodents. We were not that visual. We became visual as primates. We rediscovered trichromatic vision, etc. We re-evolved it essentially.
That's right. Yeah.
So there's all these things that happened that made us so visual, and now gazing became important. And it's a different take on one particular aspect of attention, but I think it fits the data. And of course, there's an old theory from Rizzolatti and others that attention and gaze are so tightly entwined. At least that aspect of attention is tightly entwined with gaze. Again, it's more of a physiological thing.
That aspect of attention was key.
That aspect of attention. Yeah, exactly. Because the other aspects are just different. It's like decision making.
Right.
Right.
Well, that's why I joked at first to ask you what your favorite decision making part of the brain was, thinking that you were going to want to end the call immediately. So.
No, because as you say, it's kind of like the whole brain. The hypothalamus maybe, because it's the one in charge.
Hey, you're going to end up being a hypothalamus guy, I can tell.
I might be. Yeah. And I might be studying sharks because they're unstudied. Not studied nearly enough.
Yeah, no one else is doing it. I think that's a great direction.
Well, there are people doing it, but they're not doing. There's not enough of them.
Yeah.
Right.
Yeah.
Lamprey are fantastic, though. What people do with lamprey is really important, I think.
So there's like this. We could just go down like every single topic in neuroscience and see how this sort of approach might color things, and we don't have time to do that. So for my own amusement and benefit, I want to ask you about two more. One, so I do mindfulness meditation occasionally, and thinking about the primacy of action, controlling the environment approach with respect to like something like mindfulness meditation, where you're really taking away action and you're really just perceiving and attending, quote unquote, to what you're breathing or the environment or even your thoughts. You just kind of notice them. And I wonder if you have any idea how that might connect why that would be such a beneficial thing for us, if it is, let's say, and if there could be a way to tie it into this.
I have to say I don't.
Yeah.
I really don't. And I think partially it's because it's probably related to things that we don't, that I also don't know what to say about, that it's, maybe it has to do with some, well, I don't know, some repercussions of a system that we have that deals with some aspect of prioritizing one thing versus another. But I don't know about that either. I mean,
could be like a sleep type mechanism too, where we're resetting.
Yeah, maybe. Yeah. I mean, there's a lot of, I don't think any simple theory should claim to try to explain everything. I don't have a theory for, how different things in the brain work. I have a theory about a couple of things.
Yeah.
And I have a strategy for building more theories. But I haven't built those theories. I'm not going to be the one to do that, right?
Yeah, well, these are the questions everyone's going to want to ask, because you're also going in chronological order. You're not there yet.
Yeah, I'm not there yet.
So So what about consciousness then? Do you have any speculative? You want to touch that at all?
Yeah, that one's also, you asked, when you sent me an email that said, how has your conception of consciousness changed? And I would say not at all. I still have no idea what it is. I think it's a total mystery.
Yeah.
I have an attitude about it though, and that is, let's see how things turn out with the behavior and neuroscience aspects first. And it really comes down to the analogy about life, right? A lot of people who decide to not study consciousness, like me, are using the approach saying, life used to be such a mystery. What is the special magical thing that makes living things from non-living things?
Yeah,
and it turned out asking that question didn't get anywhere. It just suddenly a question just kind of dissipated, right? As we understood more about chemistry and physiology, right? And I suspect the same thing will happen with consciousness as we address things like perspective. The fact that you have a particular perspective, and there's certain things that perspective requires of you that's different, than an external perspective. The difference between first person versus third person has to be there, because it's different to be in the control system than to be looking at a control system. So there's some aspects of it that I think are probably relatively simple, but some, like the qualia aspect, I have no idea. I don't know. But I don't think, I think it's probably something that like life will just not be a mystery once we know a bit more about other stuff.
Yeah.
So I choose deliberately to not ask that question point blank. Although I will mention again the book by Mallet and Feinberg, which took essentially my approach of looking at evolution very, very carefully to ask that question. Mm-hmm. And their answer is it still doesn't quite answer qualia, but at least they lay out some major steps. One in early vertebrates and one in parallel in birds and mammals, having to do with, complex behavior, mm-hmm. things like that. Mm-hmm. And anyway, so that book addressed that question. I don't think they answered it, but I think they took they took an approach that I thought was very promising.
Brain Inspired is a production of me and you. You can support the show through Patreon for a microscopic $2 or $4 per month. Go to braininspired.co and find the red Patreon button there. Your contribution will help sustain and improve the show and prohibit any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thanks for your support. See you next time.
The